morning. We had been looking at single phase fully controlled converter fed separately excited DC motor drive. And in the last class, we had specifically looked at continuous conduction case. So let me first of all start by drawing the circuit diagram for the single phase fully controlled converter. So here are the four thyristor devices which make up for the single phase bridge. And we are going to have the DC motor drive connected here with a constant field excitation. So the field excitation is going to be constant. So this is IF. And we are going to have the AC supply connected on this side. And as we had pointed out in the last class, we are going to neglect the source inductance effect. So there is nothing like commutation overlap. We are going to assume that the devices are ideal. So there is no voltage drop across the devices. And we are also going to assume that the turn on and turn off time of the devices are negligibly small. So those are going to be basically ideal devices. So here we are going to have this is plus and this is minus. So this is going to be the back EMF. And this machine has RA and LA as the resistance and armature inductance. And this is going to be Vm sine omega t. So this is going to be the power supply. Now we call this point as A and this point as B. This is what we said earlier. And as far as the numbering is concerned, this is going to be T1 and this is going to be T4. And these two are going to be T2 and T3 respectively. So this is the way we are numbering the devices. So we said that when current is continuous, we are going to have the armature voltage, if I may call this as VA. So if I may call this as armature voltage VA, VA average is going to be 2 Vm by pi cos alpha, where alpha is the firing angle of the converter. Okay. So in which case we said that 2 Vm, the original equation what we wrote, EB equal to VA minus IARA, from which we wrote omega equal to VA divided by K phi minus TERA divided by K phi the whole square. Now, this VA value will be replaced by this particular expression. So I'm going to write this as omega equal to 2 Vm by phi K phi cos alpha minus TERA divided by K phi the whole square. This is what we wrote in the last class. And we also said that this represents, basically, let me draw this graph, which is representing the torque speed characteristics of this motor drive. So this is going to be TE and this is omega. So we are going to have maybe at alpha equal to 0. If the characteristics are like this, as alpha increases, I'm going to have lower and lower speeds. So this corresponds to alpha equal to 0. For example, this will correspond to alpha equal to maybe 30. This is 45. And this is 60 and so on. Okay. So this is the way it is going to come down. The speed is going to come down. So if I'm looking at a particular value of TE, so at alpha equal to 0, if I am getting a speed of omega 1, and at alpha equal to 30, if I am getting a speed of omega 2 is bound to be less than omega 1. So we said that as alpha increases, right? If alpha increases, we are going to have speed decreasing at a given torque. So this is the way this drive is going to work. We also wrote the transient expression, if you may recall. We said that the equation that governs this motor drive, if I try to write, this is going to be Vm sine omega t is going to be equal to EV plus IARA plus LADIA by dt. This is going to be the equation that is governing this motor drive. So because of which I'm going to have this Vm sine omega t is positive from alpha to pi plus alpha. This is going to be the case. Whereas if I'm talking about pi plus alpha to 2 pi plus alpha, it will be minus Vm sine omega t because I will have T2 and T3 conducting. So I should say when T1 and T2, T4 are conducting. That is from alpha to pi plus alpha. So this is the duration during which T1 and T4 are conducting. Under that condition, we are going to have Vm sine omega t equal to Ra Ia plus La dia by dt plus Eb. So when we write the solution for this, it will have two particular integral portions or two of the forced responses. So that is going to be equal to one will correspond to Vm. So that is going to be Vm by Z sine omega t minus phi and minus Eb divided by Ra. These are going to be the two forced responses. And there is going to be a transient response because of this particular term that we have. So we are going to get that as plus K1 multiplied by e power minus t by tau A. Where we wrote these things also, where Z is going to be equal to R square plus omega square LA square root. And we are going to have phi is equal to tan inverse of omega LA divided by RA. That is going to be the angle by which the current is going to lag behind the voltage, the sinusoidal voltage that we are applying. And we are going to have K1 is the initial condition. Of course, tau A is going to be LA by RA. Now we said that K1 can be solved for. We said that K1 can be solved for by using the condition under steady state. We are going to have IA of alpha is going to be equal to IA of pi plus alpha. So this is going to be the condition with which you can solve for K1. So once you solve for that, that is going to give a closed form expression for IA. And if you want average value of IA, you have to calculate whatever is IA of omega t. You have to integrate between alpha and pi plus alpha. And you have to average it over pi. This is going to give us what is IA average. And this is not going to be very easy to calculate because you have so many terms, exponential terms are there, sinusoidal terms are there. So it's not going to be very easy. That is the reason generally we try to calculate this as whatever is our VA minus EB divided by RA as IA average. So both of them should be equal to each other. But this calculation is far more simple as compared to this calculation. That is the reason why generally we are going to calculate the armature current using this particular expression. So much so for the continuous conduction. So in continuous conduction, we are still not joining this characteristics to the speed axis because at this point TE is low. So IA is going to be low. So that is the reason why current will be IA will be discontinuous. During this portion, we are going to have IA to be discontinuous. I should not write capital IA. I should write, in fact, small IA because we are talking about, you know, this instantaneous current. So that is the reason we are talking about discontinuous current. Otherwise, you will not be talking about discontinuous current at all. So this is the way your characteristics are going to be. Okay. Now let us go over to discontinuous conduction. So what happens in discontinuous conduction? So during discontinuous conduction, let us say initially I am running the machine at, I'm just taking arbitrarily some value. TE is 10 Newton meter. And let us say the speed is something like 1200 RPM. Okay. So let us say IA is continuous. Maybe IA average was also 10 ampere. So this is going to be IA average. Now we are going to decrease the torque. So now reduce the torque demand without changing anything else. So we are not going to change anything else. Only we are going to modify the torque demand. So let us take some alpha also. Maybe alpha is something like 60 degrees. So this is what we have done. Now what is going to happen is, let us first of all draw the original waveform. So let us say this is the sinusoidal supply. And this is the rectified voltage in the negative half. Now this is going to be alpha. And this is pi plus alpha. Okay. Now, we are looking at the current probably increasing like this. Maybe the back EMF is somewhere here. Let me show the back EMF somewhat like this. This is the back EMF. So if I look at the current will start increasing from here itself because EB is less than VA, even during this point, even at this point where we have just fired, EB is going to be less than VA. So IA will increase. So IA will increase. So at this point, if I draw the current will increase and it will go to a peak value around here where EB and VA are equal to each other, and then it will come down. So it has come down and again it will increase, it will come down and so on. So this is continuous conduction. But now we are decreasing the torque. So the current is going to go down further and further. So the next value of current could be something like this. So it may increase until this portion and then come down and again increase and come down and so on. So this is reduced IA. So this is the reduced IA value. So when I try to decrease it even further, when I want to decrease it even further, maybe I'm going to have the current increasing like this. And I'm going to see that we are having, less value of conduction interval also. So the current might come down to 0 right here. And then it has to again start from here. It has to go to a maximum value and it has to come down right here. So this is going to be IA, which is in this continuous conduction zone. So when I try to reduce the torque further and further, the natural characteristics in your separately excited DC motor tells that as the torque decreases in this direction, the speed increases as the torque decreases. Okay, so this is what we said already. So this is TE and this is omega. So when we decrease the torque demand, IA is going to decrease. But if IA is decreasing, then in that case, we are going to have EB slightly increasing. If EB increases, in that case, you are going to see that the opposition to the current flow, that is also going to increase. So what I mean is, these are the 4 devices which are bound to conduct alternately, depending upon which one is being fired. And if I'm going to have the back EMF here, which is actually opposing the flow of current, this is going to be plus and minus, this is the back EMF, in which case we are going to see that if the back EMF decreases, the opposition is going to decrease. But if the back EMF increases, the opposition is also increasing. So the current will actually diminish further and further. So you're going to see that generally with reduction in the torque, and when you especially approach discontinuous conduction, you're going to see that normally the speed variation becomes more and more because of the fact that the back EMF also is going to increase and it is going to oppose the current flow even more at this point in time. So let us try to look at now. There are 2 cases of discontinuous conduction that we are going to look at. One is when alpha is less than gamma. The other one is alpha is greater than gamma, where gamma is actually the intersection point between EB and VA. So gamma is going to be the intersection point. So this is essentially Vm sine omega t, which is actually gamma. So Vm sine gamma is equal to Eb. So gamma is going to be Eb divided by Vm sine inverse of that. So we are going to have gamma to be sine inverse of Eb divided by Vm. This is going to be the gamma value. So we are going to look at 2 cases where alpha is less than gamma and alpha is greater than gamma. So let me draw this waveform corresponding to, first of all, alpha greater than gamma. So let us say I'm going to have this as the sine wave and this is omega t. So this is Vm sine omega t. Okay. And I'm going to draw for the case of alpha greater than gamma. This is what I'm going to draw. So in which case, let me draw first of all back EMF also. So back EMF is going to be somewhat like this. This is a constant value. So let me draw the rectified voltage as well. So this is the rectified voltage. And I am assuming this is gamma, this point where EB and VA are intersecting with each other. So this is gamma. And we want alpha to be greater than gamma. So I'm going to assume alpha is somewhere here. So this is going to be alpha. So obviously I'm going to have pi plus alpha somewhere here. So I'm going to fire T1 and T4 at this point, and I'm going to fire T2 and T3 at this point. Okay, so look at the circuit. So T2 and T3 will be fired at this point, exactly symmetrically after pi radians in the negative half side. So if we say this is discontinuous conduction, at the time of firing the device, I'm going to have alpha equal to 0 degree, current equal to 0 when the devices are fired. So if I say IA of alpha is going to be 0, that is what we mean by discontinuous conduction. So I'm going to have actually armature current increasing slowly, and it will be reaching the peak approximately when EB and Vm sin omega t intersect each other. So this is going to be the kind of current waveform I will have. So the current is increasing like this, and it might come down and reach 0 before pi plus alpha. So before the next pair of devices are fired, it is going to reach 0. So this is IA. So what I have drawn in black color is going to be IA. So it will repeat itself again. I'm going to have this increasing like this, and it will come down like this. So this is again IE. So I'm going to have T2 and T3 conducting only for so long. And similarly, T1 and T4 conducting only for so long. So I'm going to call this particular point as beta, where the current discontinuity occurs. That point I'm calling as beta. So obviously, I should say by symmetry, this is pi plus beta. This point is going to be pi plus beta. Okay. So I will have the voltage, what is appearing across the armature, that is going to appear during this portion. From here, all this and until this point. So this is going to be the armature voltage. And from this beta to pi plus alpha, there is no current. IA, what is flowing originally, what was flowing originally, that has become 0. So this is going to come up as open circuit voltage. So if I actually draw how the waveform looks like for the armature side, so it is going to jump like this. It is going to have a waveform which is going like this. So until here, it will follow the sinusoidal voltage. But after that, it is going to jump up to EB. And from EB, it is going to again jump up to the value which is corresponding to minus Vm sin omega t. So I should say there are specifically 3 intervals. I should say from alpha to pi, it is Vm sin omega t. In fact, it's not only alpha to pi, alpha to beta. So there are only 2 intervals. This is going to be alpha to beta. VA is going to be equal to Vm sin omega t. And from beta to pi plus alpha, VA is going to be equal to EB. Armature terminal voltage will be same as that of back EMF because it is in open circuit condition. So if I want VA average value should be equal to, now I should say alpha to beta, Vm sin omega t d omega t plus beta to pi plus alpha EB d omega t. whole thing averaged over pi. That is what is going to be my overall VA value. So this is going to be the VA value. So I should be able to write this as 1 by pi and VM sine integration is minus cosine. So I'm going to have a cos of alpha minus cos of beta. Okay. So this is going to be the first portion's integration. The next one is going to be EB multiplied by pi plus alpha minus beta. So this is going to be the overall expression for armature voltage. Please note the armature voltage expression in continuous conduction case was very simple. It was only having 2 Vm by pi cos alpha, and this was like a constant at a given value of supply voltage and at a given value of firing angle. This was a constant. There was no problem at all. Whereas in this particular case, if I am trying to look at it, beta is coming into picture everywhere and back EMF is also coming into picture. Back EMF is not a big deal because that is anyway a constant we are assuming at a given speed. But beta is the problematic member of this entire equation. It is not going to be very easy to determine beta. So let us try to see how to determine beta. So how to determine beta? So to determine beta, first of all, we'll have to solve the transient equation. So let me write down again the transient equation, which is Vm sine omega t is equal to Ia Ra plus La dia by dt plus Eb. Okay. Now this is the transient equation which we wrote even in continuous conduction case, but only thing is this is for omega t ranging between alpha and beta, not really pi plus alpha, because we are having literally zero voltage after or back EMF as the only voltage that is appearing across the armature terminal from beta, this duration, that is from beta to pi plus alpha. So this is beta to pi plus alpha. This duration we are going to have only back EMF appearing. So this Vm sine omega t appears across the armature only from alpha to beta. Now if I try to write the solution, Ia of omega t is going to be again Vm divided by Z sine omega t minus phi minus Eb divided by Ra plus K1 into e power minus t by tau A. All these things are still valid, but for getting K1 value, the initial condition is, please note that Ia is 0 at this point. So I should say Ia of alpha equal to 0. So for getting K1 value, we have to actually substitute an initial condition which is corresponding to Ia of alpha equal to 0. So if I say basically in this particular expression, Ia of alpha, which is equal to Vm divided by Z sine of alpha minus phi, because omega t is alpha, minus Eb divided by Ra plus K1. You can say omega t. Omega t is basically alpha. So e power minus alpha divided by omega tau A. So this is equal to 0. So I should say K1 into e power minus alpha by omega tau A equal to EB divided by RA minus VM divided by Z sine alpha minus 5. So in which case I should be able to write what is K1. Of course, K1 will have a pretty long expression. So this entire closed form expression for IA of omega t becomes even more complex in discontinuous conduction case. So it is going to be pretty complex. So it is not going to be very easy to first of all evaluate IA of omega t. After evaluating or after getting an expression for IA of omega t, you can say that at beta, again the current becomes zero. So the current hits zero at 2 points. One is at alpha itself. At alpha, the current is going to hit zero. Another point is at beta. So 2 points, the current is going to hit zero at alpha and beta. Already we had used this IA of alpha equal to 0 to solve for K1. So we can again use IA of omega t equal to 0 when omega t is equal to beta. So we can actually equate IA of omega t to 0 and solve for omega t, which will actually come out to be beta. But it is not going to be very easy to solve an expression which is consisting of exponential, sinusoidal, trigonometric terms and things like that. So beta can be solved only by using an iterative technique. So we need to use an iterative technique like Newton-Raphson method or something where you will assume a reasonable value of beta, maybe close to pi or something, and then you will keep iterating it by looking at what is the error you are getting. So from that, you will be able to arrive at the actual value of beta. So discontinuous conduction case actually introduces a new variable, which is beta, which is the point of discontinuity, point of discontinuity of IA. So this becomes a very difficult situation to solve for beta. And that is the reason why we may not be able to arrive at the speed very easily, because we will not be able to calculate even VA average easily. If we don't calculate VA average easily, then it's not going to be easy for us to solve for the speed, because speed happens to be VA divided by K5 minus TERA divided by K5 square. So VA itself is not easy to solve. So it is not going to be easy for us to solve for this P. It's not going to be easy at all. So this is one of the major problems with discontinuous conduction, and that is the reason why many times in DC motor drives, we try to avoid discontinuous conduction, probably by including an additional inductance. So if I try to include a little larger inductance here, along with the armature inductance, then that will take care of making the current continuous. Or another way to do it is maybe TE cannot be less than a certain value. We are going to say TE cannot be less than a certain value. If we do that, then the armature current drawn will be somewhat larger. In that case, we are going to have continuous conduction. We are not going to have discontinuous conduction at all. So this is one case of discontinuous conduction. One more thing we might like to kind of, dwell upon this time is, if our value of current becomes lower and lower, if we are going to have more and more reduction in the current, then the beta value initially, so I can just draw this waveform once again. I am going to have this as the sinusoidal waveform for the supply, and current is starting from alpha and it is increasing like this and it is coming down at beta. Okay. Now, if I try to decrease the torque demand further, I'm going to have actually the current again starting here, but the current is becoming smaller, means beta will also decrease. So we are going to have beta decreasing as TE decreases. If TE decreases and beta decreases, then you can see that as long as beta was at this point, this portion of the negative voltage was appearing when I calculated VA. So when I calculated VA, what I did was from alpha to beta, completely I integrated this particular voltage to get what is VA average. So VA average we calculated as from alpha to beta, what is Vm sin omega t. So from pi to beta, it is going to be negative. So if beta is decreasing, so if beta decreases, negative portion of VA, small VA comes down. So overall VA value, average value will increase because the negative portion was actually cutting into the positive portion. So whatever is the positive portion, from that you have to subtract this negative portion. And of course, you are going to have a second portion which is corresponding to beta to pi plus alpha EB. So if beta has decreased, EB's contribution is also going to increase. So overall, we are going to have, reduction in the voltage. Whatever was the average armature voltage earlier, compared to that, now the average armature voltage will increase. It is going to increase, because of which I will have a good amount of increase in speed. So in discontinuous conduction zone, due to reduction in the torque, so the speed is going to increase due to two reasons. So speed increases during TE reduction due to two reasons. One is inherently when TE decreases, speed increases in the speed torque characteristics of the separately excited DC motor itself. And second thing is beta will come down. So negative portion of Vm sin omega t included in VA decreases. Also, EV portion included in VA increases. So both these things are going to contribute to speed increase. So both these factors are going to contribute to speed increase. That is the reason why speed regulation in discontinuous conduction is more. So if I am going to reduce the torque from 5 Newton meter to 4 Newton meter in continuous conduction, whereas in discontinuous conduction, I am doing the same reduction in torque from 5 Newton meter to 4 Newton meter, the speed increase in continuous conduction may be 100 RPM, whereas the speed increase in discontinuous conduction may be 150 RPM. So speed regulation in discontinuous conduction is more. So this is not really a good thing. So we may not be able to maintaining constant speed is going to be a problem in even more of a problem in discontinuous conduction. So maintaining constant speed is going to be not easy in discontinuous conduction. So in general, discontinuous conduction is avoided because of these reasons. You don't have a straightforward relationship between speed and torque, and you are not probably in a position to maintain the speed at a constant value very easily because discontinuous conduction takes a toll on the speed regulation in general. That is the reason. Okay. Now let us look at the case of discontinuous conduction where alpha is less than gamma. So we are going to look at the discontinuous conduction case where alpha is going to be less than gamma. So let me again draw the circuit of the fully controlled rectifier. And I'm going to include the separately excited DC motor here. Once you understand the single phase converter, it is going to be pretty easy for the three phase converter. So we can go definitely faster in three phase converter case. Let's first of all, look at this single phase converter thoroughly. So this is Vm sine omega t. And this point is going to be A and this point is going to be B. This is T1, this is T4, this is T3 and this is T2 and this is going to be the back end. Now we are looking at alpha less than gamma. So let me first of all draw the sinusoid. So this is the sinusoid and let me draw the rectified sinusoid also during the negative half cycle. Now let me say probably the back EMF is somewhere here. So this is back EMF. And obviously I'm going to have that means gamma here. And alpha is less than gamma. So if alpha is less than gamma, in all probability EB is very high. So probably we have reduced the torque considerably. That is the reason why the speed has increased and EB is high. So we are going to have alpha somewhere here. Let me show this as alpha and let me show this as pi plus alpha. Okay. So we are going to have, if I am firing the device at this point and it is discontinuous conduction, mind you. So that means the current in all probability must have reached zero here. The current must have reached zero here. So at this point, if I am looking at the voltage across, so this is firing T1 and T4. There is no current here. The current is zero. And if I look at what is the voltage that is coming up at this point for T1, this is going to be EB. And this is corresponding to Vm sine omega t. So this point A is Vm sine omega t and point, if I may call this as some N, that is going to be EB. So EB happens to be greater than Vm sine omega t at this point because this is our Vm sine omega t. So Vm sine omega t is clearly smaller than EB. So at alpha, omega t equal to alpha. At omega t equal to alpha, EB is greater than Vm sine omega t. So T1 is reverse biased. So it cannot conduct. See, this is one reason why in none of these converters, we'll just give only one single pulse. We tend to give a large train of pulses. So if it is like alpha at this point and pi plus alpha at this point, we'll give multiple pulses like this. So many pulses will be given to this particular device, T1 and T4. So I will have multiple pulses being given from right from alpha until pi plus alpha. So these are the train of pulses for T1 and T4. So if the device is not getting fired at alpha, so T1 will not conduct at alpha. But at gamma, VA and EB are equal to each other. Vm sin omega t and EB are equal to each other at this point. So at that point, your device will get forward biased. So you can say that at omega t equal to gamma, T1 and T4 get forward biased. So they will start conducting. So once they start conducting, you're going to have an increase in the current. So the current is going to start from gamma, not from alpha. So the current will start like this, and it might increase until this portion where Vm sin omega t equal to EB, and then it will come down drastically like this. So this is the way I'm going to have the current. So this here also the current will increase like this and then come down like this. So this is going to be our IA. So in this particular case, if I try to write the expression for average value of VA, so VA average will have basically, so please note, this is coming down here at this point. So this is beta. So I have to write this is coming down at beta. So this is pi plus beta. And after that is going to be alpha. So alpha is actually you are going to have this like this. Beta is less than pi plus alpha. And this pi plus alpha is going to be again less than pi plus gamma because alpha is less than gamma. So this is the kind of relationship you have. So you are going to have actually VA average, you have to take from gamma until beta because until where the current is coming up. So this is going to be the entire voltage that comes up until beta. So until beta, this will come up. Okay. And after that, from beta onwards, it will jump to back EMF. So we are going to have gamma to beta Vm sin omega t, d omega t, plus beta to pi plus gamma EB d omega t. So here also beta is involved. Whether you like it or not, you have to involve beta to get the value of average armature voltage. So just to expand and draw this, this is going to be the positive half cycle. So this is omega t. And this is coming down like this. Now we are going to have alpha somewhere here. And if I say that back EMF is here, so this is going to be gamma. So from here, the current is going to increase. It will increase and it will reach the peak value and it will come down maybe somewhere here. So this is beta. After this beta, what comes is pi plus alpha. And further, if I try to draw here, this is where if I try to draw the rectified sinusoid, it will be somewhat like this. So this point is pi plus gamma. This point is pi plus gamma. So if I am looking at the output voltage is going to start from gamma and it will go through this entire region and it will come until beta. So until this point, it is going to come. So this portion is where T1 and T4 conduct from gamma to beta. That is where it is going to conduct. So this is going to be VA average, and it's not going to be easy to calculate this either because beta is coming up in this particular portion as well. That is the reason it's not going to be easy to calculate. So in this particular case, we can have again Vm by Z sine omega t minus phi minus EB by RA plus K1 multiplied by E power minus T by tau A. This is going to be IA of omega T when we are looking at omega T lying between gamma and beta. And here we can solve for K1 by using the initial condition. In this case, the current starts only at gamma. So when IA of gamma equal to 0, this is going to be the initial condition. Okay. So this yields a complete expression for IA of omega t. Now, to obtain beta, substitute in the complete expression for IA of omega t. You have to basically substitute IA of omega t equal to 0 when omega t is equal to beta. So when omega t is gamma, the current is 0. When omega t is beta, also the current is 0. Only thing is IA of gamma equal to 0 we are using as initial condition, whereas IA of beta equal to 0 we are using for solving for beta. Again, this has to be solved for. This can be solved for by using iterative technique. So this is also not easy to solve. So this is going to be one of the cases of discontinuous conduction when alpha is less than gamma. There could be another, kind of alpha less than gamma case also. So let me take that up. This continuous conduction for alpha less than gamma. This is case 2. So let me first of all again show the sinusoidal voltage somewhat like this. Okay, so this is the applied voltage. Now we said that the back EMF is somewhere here. So I'm going to show the back EMF as a pretty high value. Now this corresponds to EM. And this is EB. Okay. Now this is going to be gamma. And this is going to be pi plus gamma. So I'm going to take alpha such that alpha is somewhere here. And this is going to be pi plus alpha. So this is pi plus alpha and this is alpha. Okay. Now we said that the device will start conducting T1 and T4 will start conducting only at gamma. So I'm going to draw the current now. the current will increase like this, we said, and it is going to go until here. So it can continue to conduct and it will reach its peak somewhere here. And from here, it is going to come down. And when it is coming down, it is not necessary that it has to come down at pi plus alpha itself. In fact, it can come down after that also. So this can be beta. So let us try to analyze whether it is possible at all. So you are looking at, this is the sinusoidal voltage, and you are having T1 here, and you are having the DC motor drive here, and you are having T4 here. So this is conducting like this, and this is finishing up its path somewhat like this. So this is T4. So this is the way it was conducting. Now, what we are doing is at pi plus alpha, at this point, T1 and T4 were fired. So T1 and T4 started conducting here. That's what we thought. And it will continue to conduct probably until this point, not beyond this. Because once the current is continuous, irrespective of whether EB is greater than Vm sin omega t or EB is less than sin omega t, I have to look at this particular device. This is T2, T3, and this is going to be T2. I'm going to have T2 here. Okay, so this is T1 and this is T2. Sorry, this is not joined here. So this is T2. So this is T1 and this is T2, and this is getting connected here. So this is what it is. Now, when I look at T3, if already the current is flowing, EB has nothing to do with that because T1 is a short circuit, T4 is also a short circuit, and this is A and this is B, and already the sinusoid has entered its negative half cycle. So I'm going to have this as plus and this as minus. So this plus will come here and this minus will come here. So that is the case as far as T2 and T3 both are concerned. So in this particular case, when beta is greater than pi plus alpha, IA is still not 0. So at pi plus alpha, T2 and T3 will be forward biased. So they will conduct. So they will conduct. So what we are going to have now are three different portions of the voltage. We are going to have from gamma, this entire voltage will come up. And until pi plus alpha, it will be negative voltage. But from pi plus alpha to beta, it is going to be the reverse of Vm sin omega. And still, that Vm sin omega t minus Vm sin omega t is still magnitude-wise smaller than EB. EB is here, whereas Vm sin omega t is here. So the current will still continue to decrease. So from pi plus alpha to beta, minus Vm sin omega t will appear as VA. But still, Vm sin omega t magnitude is smaller than EB. So IA will continue to decrease. Okay. So because of which at beta, IA reaches 0 value. So the current becomes discontinuous. So once it reaches 0 value, the devices are not going to be able to conduct anymore. So T3 and T2 will go off. Once T3 and T2 will go off, but you are still giving pulses for 180 degrees. From pi plus alpha to 2 pi plus alpha, you will be giving pulses. From this point, pi plus alpha until 2 pi plus alpha, you will be giving a continuous train of pulses. So this is going to be for T2 and T3, because of which they will again start conducting at pi plus gamma, because they will get forward biased and they will also have the pulses at pi plus gamma. So again, the current will increase and it will decrease. So this is the way IA is going to be. So this has very clearly three portions of voltages. First portion is Vm sin omega t. Second portion is minus Vm sin omega t. And third portion is EB. So we are going to have actually VA average. If I try to calculate VA average value, will have Vm sin omega t integrated from gamma until pi plus alpha. Okay. Then we are going to have from pi plus alpha to beta, it is going to be minus Vm sin omega t. And from beta until pi plus gamma, it is going to be EB. So these are going to be the three portions that come up, which have to be averaged over pi. So we will have specifically three portions being integrated ultimately to arrive at what is the value of average VA. And from average VA, you should be able to calculate what is the speed. But it is not going to be easy, because again, it involves beta everywhere. Because it involves beta, it is not going to be easy to calculate this. So what we looked at in discontinuous conduction case motoring portion was alpha greater than gamma and alpha less than gamma. Two cases. First of all, alpha greater than gamma and alpha less than gamma. In alpha greater than gamma, we are going to have basically IA of alpha equal to 0 as the initial condition. Whereas in the case of alpha greater less than gamma, we are going to have IA of gamma equal to 0 as the initial condition. But in alpha less than gamma, there could be two cases where beta can lie between pi plus gamma and pi plus alpha. This is what we saw at last. Or beta can be less than pi plus alpha. So these are the two cases we looked at for alpha less than gamma itself. Now that we have seen different cases of discontinuous conduction, we are ready to now draw the speed torque characteristics for this particular separately excited DC motor drive. So we will be looking at speed torque characteristics for the separately excited DC motor drive in totality. And we will also be looking at regenerative braking operation in the next.